Modeling an ideal gas. Can we derive the ideal gas equation from theory? We can do this if we use what is known as the kinetic theory of gases, which is based on a number of assumptions. We assume that gas molecules are in constant random motion, that all these molecules have equal mass, me, that the number of molecules, n, in a gas is very large, that molecules collide perfectly elastically, so that momentum is conserved when they collide with each other, that no force acts on the molecules except during collisions, which means that we are neglecting all long-range electrical or magnetic forces. We assume that molecules are point masses, which have negligible volume, and so the only form of energy that they possess is translational kinetic energy. There's no energy associated with spin or vibration of molecules. Using these assumptions, we can simulate the behavior of an ideal gas in which molecules are hard spheres which collide with each other and with the walls of the container. They exert a force when they impact on the walls, and this is what we experience as gas pressure. Now, if we increase the volume, then the frequency with which the molecules are impacting on the walls decreases because there's a much larger surface area. And therefore, there's a longer interval between impacts and the pressure is reduced. So this explains why Boyle's law behaves the way it does. Now we can calculate the force exerted by a single molecule on the wall. If we use Newton's law, we know that the force on the wall is minus the rate of change of momentum of the molecule. Once the molecule hits and rebounds off a wall, the velocity before impact was c. The components of this are cx and cy in the x and y direction respectively. After impact, this speed c is unchanged. The component cy remains the same, but the component cx has now become negative of what it was before the impact. So the change in the x momentum of the molecule, delta p, is given by the final momentum, which is me times minus cx, and from that we subtract the initial momentum, which is me times cx. So delta p is minus 2 me cx. Now, after it hits a wall, the molecule rebounds, hits the opposite wall, and then comes back. It travels a distance L across the width of the container. The time taken to travel once across the box, delta t, is L over cx. But the molecule has to travel twice across the box, so the interval between impacts on the same wall is 2 delta t. The force on the wall, therefore, is minus delta p divided by 2 delta t. This is the rate of change of momentum. Substituting values for delta p and delta t, the force on the wall is me cx squared by L. Now, if we want to calculate the force of n molecules, which there are in the gas on the wall, we can sum up all of these contributions. So we get me cx1 square plus me cx2 square, and so on until me cxn square divided by L. The pressure equals the force divided by the area. So we take this term for the force and we divide that by the area of the wall, which is L square. If we now simplify this and multiply it by n and divide it by n, where n is the number of molecules. The reason we do this is this term cx1 square plus cx2 square up to cxn square divided by n is an average velocity. And this is what we define as the root mean square, the RMS velocity. Cx RMS equals Cx1 square plus Cx2 square all the way up to Cxn square divided by n. And we take the square root of that. N times Me is just the mass of the gas. N is the number of molecules, Me is the mass of one molecule. L cube is the volume of the container, so that is the volume of the gas, V. Substituting that, we get the pressure equals M divided by V times Cx square. Now, the velocity, the RMS velocity, C RMS square, is equal to the sum of the three components, Cx RMS square plus Cy RMS square plus Cz RMS square. But these velocities are random, so there's really no difference between the x, y, and z directions. Therefore, the average value of the components in all the directions should be the same. So we can say that all the components are equal to each other. In which case, C RMS square is simply 3 times Cx RMS square. Now we can take this and substitute this into our expression for the pressure. And the pressure becomes 1/3 M over V C RMS square, where now instead of just the x component, we have the molecular velocity, the average molecular velocity, C RMS. M is the number of moles, N, times the molar mass, M. So let's substitute that and write our equation as PV is equal to 1/3 NM CRMS square. The reason we do this is that this is now starting to look like our ideal gas equation. PV is equal to N RUT. And indeed, it would be exactly equal to the ideal gas equation if the right-hand side equals 1/3 Nm CRMS square. Now we can cancel out N, and we have to satisfy this condition that M CRMS square is equal to 3 RUT. Now let's divide both sides by the Avogadro's number, Na. And the reason we do this is that on the left now, this M divided by Na, this is the molar mass, which remember is the mass of an Avogadro's number of molecules. If we divide that by Avogadro's number Na, we simply get the mass of one molecule, Me. Ru upon Na is what we define as being equal to the Boltzmann constant. So this is another universal constant which has a value of 1.38 into 10 to the power minus 23 joules per Kelvin. We now have Me CRMS square is equal to 3 kT. The left-hand side is starting to look like a kinetic energy term. And to make it equal to the kinetic energy, we multiply the equation by half. The left is now the average kinetic energy of a single molecule. And this equals 3 over 2 kT, where k is a constant. So this gives us an understanding of what the temperature means if we are looking at it at a molecular level. The temperature is a measure of the average kinetic energy of a gas molecule. So as we increase the temperature of a gas, the velocity of the molecules should start increasing. So if we do our simulation of a gas at 300 Kelvin, the molecules are moving at a certain average velocity and they're exerting a certain pressure. If we raise the temperature to 800 Kelvin, the molecules are moving much faster, which means that the frequency of impact on the wall is increasing, and therefore the pressure is increasing. And this explains why we see Charles's law. To summarize, an ideal gas can be modeled using a simple model of molecules as colliding spheres. The kinetic energy of molecules is proportional to the temperature.